Welcome to the 2018 AP Physics C Electricity and Magnetism free response questions. Without further ado, let's get straight into it. Alright, you've got our equation sheets up here, so nice useful equations. Let's try to do the actual questions. So question 1, a solid plastic sphere of radius A and a conducting spherical shell of inner radius B and outer radius C are shown in the figure above. The shell has an unknown charge. The solid plastic sphere has a charge per unit volume given by rho of r's beta r, where beta is a positive constant and r is the distance from the center of the sphere. Express your answers to part A, B, and C in terms of beta, r, a, and physical constants as appropriate. You got some kind of non-conducting sphere and then some kind of conducting spherical shell. 3 different radii. Question 1. Oh my goodness, sorry. Question 1, part A, is just asking us to consider a Gaussian sphere of radius r concentric with a plastic sphere and derive the charge enclosed by the Gaussian sphere for the following regions. So the first region we've got for r less than or equal to a, well, we have this rho of r. So the charge density is going to be the integral from 0 to r of 4 pi r squared rho of r dr. This is in turn just going to be 4 pi, because rho of r is beta, we just take out that beta, integral of 0 to r of r cubed dr. Then we just go ahead and evaluate this integral, and what we get is 4 pi r cubed beta over 3. This is going to be our expression for the charge contained for part I. For part II, matey, we have for r between A and B. Between A and B, there's actually no charge, it's just air. So what we can say is set r to be A, and that's going to be the total amount of charge. And so we get Q equals 4 pi big R cubed beta over 3. This is going to be just setting r equal to A. And I realize I put big R cubed. I meant A cubed here. So let's see if we can just get a nice erase going. Nice. Alright, for B, pretty good on time. We're going to use Gauss's law to derive an expression for the magnitude of the electric field of the following regions. The same 2 regions. So for part I, we have Gauss's law, which you get to just write out the equation. So we've got Gauss's law is the enclosed charge. I guess I should write charge enclosed here to be extra clear. The enclosed charge over epsilon 0. In this case, because we're on an equipotential, we have E times 4 pi r squared. E is going to be constant. So for part I, we're between 0 and a, so we have 4 pi r cubed beta over 3. That answer to part AI over epsilon 0. And we divide by 4 pi, get rid of that. We divide by the r squared, and our final result for BI is that the electric field increases linearly as r beta over 3 epsilon 0. Let's switch the colors to stop the monotony. For part II, we have very similar mechanics. We have similarly Gauss's law, E dot dA, equaling the enclosed charge over epsilon 0. Basically, that flux is constant if you have the same charge. And then by this, we get that, again, E times the surface area of that Gaussian sphere that we're dealing with, 4 pi r squared, is going to be the charge enclosed, but this time that's going to be 4 pi a cubed beta over 3 over epsilon 0. And so we get that for BII, we get the 4 pi's go away, and we get that it is decreasing with respect to r squared. So we get a cubed beta over 3 epsilon 0 r squared. Let me just make sure I have not made any silly mistakes right off the bat. Looks like we're good for the first part because things are lining up. And that over 3, does that over 3 make sense? Yeah, I think it does, because it has to do... Ooh, wait a minute. Right, we get the over 3 because it's not a uniform charge density. Okay. Yeah, I'm good with that. Cool. Let's move on. On the axes below, sketch the electric field E as a function of distance r from the center of the sphere. Sketch the graph for the range r equals 0 at the center of the sphere to r equals c, the outside of the conducting shell. Alright, let's throw up some axes here. So we've got, and we should write that this is in response to part D. We've got E going up here. We've got R here. You've got A, B, and C. And on the actual test, you would, of course, be just drawing this all on the paper. Between 0 and A, we see that the electric field as a function of R increases linearly. So we can draw it starting from 0 and going to some kind of constant. And then it drops off. Sorry, it does not drop off. It, between 0 and A, it drops, yes it does, but not discontinuously. It drops off by a square, so you get like a little inverse parabola here. And then at B, because now we're inside of a conductor, we drop off immediately to 0. So we get going at 0 for some time there. And then at the end of C, because the conductor was neutral, I think they said, right? The shell has an unknown charge. Oh, ha, we skipped part C. I think that would matter. Let's move all of part D much further down and focus on part C before we jump the gun. Probably should not do that on the actual test. Just a thought. At any point outside of the conducting shell, it is observed that the magnitude of the electric field is 0. Interesting. That means that the conducting shell has opposite charge to the plastic sphere. So determine the charge on the inner surface of the, so remember, the total charge on the outside, so this is on the conducting, is equal to the negative charge on the plastic. This is because it must cancel out in the end by Gauss's law. So this is not question 1, this is part C. I'm messing up on all fronts. Alright, we're still pretty good on time. So determine the charge on the inner surface of the conducting shell. Remember that on inside of a conductor, the electric field is 0. So the inner surface must completely cancel out the charge in the plastic sphere. So the charge on the inner surface is going to be equal to negative the charge on the plastic. And what is the charge on the plastic? The charge on the plastic is the charge that we derived in A2. So the total charge on the inner surface here is going to be 4 pi a cubed beta over 3. 4 pi a cubed, not a pi. 4 pi beta a cubed over 3, right? Yeah, that looks good. And then for part 2, we have determined the charge on the outer surface of the conducting shell. Well, remember, we are given that the magnitude of the electric field is 0 outside of the shell. So what that means is that somehow the shell must cancel out the sphere. That means that the total charge on the conductor must be negative the charge on the plastic. All that negative charge just so happens to be on the inside. So because the total charge on the conductor, which equals the charge on the inner surface plus the charge on the outer surface, equals, and sorry, this has to be negative, equals negative 4 pi a cubed beta over 3. This implies that the charge on the outer surface is just 0. Now let's actually move on to part D. So within the conductor, we know automatically that the electric field is going to be 0, and they're just giving us that the electric field is also 0 on the outside of the conductor. So let's just make that a nice thick line so they can tell exactly what's happening. It's like Now, the figure below shows the sphere and shell with 4 labeled points. Oh, wait a minute. The electric field. Yeah, okay, we're good. Are we... I'm trying to think, because the electric field here is not necessarily going to need all the charge to cancel that out. Yes, it will need all the charge to cancel that out. Never mind, we're good. D part 2, so this is actually just part I. D part II has us doing the figure shows below shows the sphere and shell at 4 points W, X, Y, Z. Point X is on the surface of the sphere. Point Y and Z are in the inner and outer surfaces of the shell. Blah, blah, blah. Oh, and W is the center. Rank the points according to the electric potential at that point, with 1 indicating the largest. And if they have the same, give them the same numerical ranking. Cool. So let's get W, X, Y, Z. So we know that beta is a positive constant. That's very important, because what it tells us about our diagram, if we were to just draw out the diagram here, is that the inner sphere is positively charged and the outer sphere is negatively charged. So which point will have the highest electric potential is going to be W, because W is furthest buried inside. Well, actually, let's consider this. So your potential difference is essentially equivalent to how much electric field you have to overcome. So the electric field is 0 after B. So that tells us that Y and Z are going to be equivalent. Y equals Z. On the other hand, you do need to overcome a certain electric field to get to point A, which means that X is going to be greater than whatever that is, and you gotta overcome a little bit more electric field to get to W. So W is going to take the number 1 spot, X is going to take the number 2 spot, and Y and Z are going to tie for the number 3 spot. That is our final answer. And rather than thinking about it more, let's move on so that we get some nice time bonus. Alright, let's just scroll all the way up here and start anew. Great. Question 2. An experiment is designed to measure the dielectric constant of paper that has an area of blah. Using aluminum foil, 2 parallel plates are created with the same area as the paper. 500 sheets of paper are placed between the aluminum foil plates to create a parallel plate capacitor shown in the figure above. You've got some multimeter. This is going to measure voltage and current. Aluminum foil on the outside, paper on the inside. Using a multimeter, the capacitance C of the capacitor is measured. The number of sheets and the total thickness D of the stack of paper are recorded. Lots of passive voice. The experiment is repeated, noting the number of sheets of paper each time. The data are recorded in the table below. So you've got sheets of paper, different distances, different capacitances. Let us indicate that we are in question 2, part A. Indicate below which quantity should be graphed to yield a straight line whose slope could be used to calculate a numerical value for the dielectric constants of paper. Remember that the final capacitance is equal to the dielectric constant times the distance apart divided by, let's check that. I think I have D and A possibly reversed. Yeah, I do have them reversed. So ignore what I said here. It is equal to this times epsilon 0, sure, if you wanted to find it that way, A over D, which makes much more sense. So if we were to, if we were to find a straight line whose slope could be used to calculate a numerical value for the dielectric constant of paper, we're trying to find this thing. We want to consider A over D as our quantity. And we know the capacitance, so what we can say is that capacitance equals A epsilon 0 over D times K naught. And so if we consider k naught to be some slope, then a epsilon 0 over d is going to be the other thing. Actually, what we should really do is we should say that this is going to be k naught epsilon 0 times a over d. Bam. So for the, let's write this out, for the vertical axis, we're going to be considering the capacitance in farads. And for the horizontal component, we're going to be considering A over D. A over D, which is meters squared over meters, which is meters. And what we're going to get is that the y equals some slope times the x over d. Cool. Use the remaining columns of the table that I'm going to have to write myself to, so let's use a nice white for our table. All right. And so this is the 500, the 400, the 300, the 200, the 100. A over D. Didn't bring a calculator, so I'm going to just cheat and do it in the Google search bar. A over D is going to be 0.060 divided by D, which is first going to be 0.045. So that's going to give us 1.33333333. Next, it's going to be over 0.36. It's going to give us 1.666666666. All right. It would have been good to actually bring a calculator to the recording session. Two. Next is 200 sheets of paper at 1/8, 3.3333333333. And finally 0.16. Now that's odd. It almost seems logarithmic. But the capacitance is changing like that also. So we should be good. All right. Use the remaining columns of the table. So we're done with part A. Part B. Plot. Plot, plot, plot. Let us make a nice plot. Maybe here will do. So here we're going to have A over D, which we're measuring in meters. Here we're going to have capacitance, which is in farads. And for the A over D, we're going to be going from 0 to 6. So here's going to be 6, 3, 4, 5, 2, 1. And for the farads, capacitance, we're going to be going from 6.5 to 21, but on quite a scale. 6.5 times 10 to the negative 11th, up to 21.5, no, just 21, up to 21 times 10 to the negative 11th. And in the middle here, we're going to have 27.5 over 2 is 13.25. 13.25. 0.25 times 10 to the negative 11th, and that should give us a pretty decent idea of where we're at. All right. Plot the data below. All right. Draw a straight line that best represents the data. So for the first one, we're going to have the x position be 1.33. 1.33. Let's do this in red so we can see it. And the y position be 6.5. So we're going to have a data point right there. For the next, we're going to have 1.666, which is there, and 7.4, which is going to be there-ish. I should have scaled this better. This would be easier if I just had their graph. Then we have 2.222 and 8.9. So we can put that about there. Next we have 11.9 as the y with 3.333. 11.9 goes almost all the way up here. And finally we have at 6, 21. So it's the very final balance. So we can see that we are increasing exponentially somehow. And drawing in that line of best fit looks about like that. Except at 0 we need it to be 0. So let's start it at 0. Great. And draw a straight line. Using the straight line, compute a dielectric constant for the paper. So what we did is we said that slope is equal to, if I recall, slope is equal to the dielectric constant times epsilon 0. Let's calculate this slope. The slope is the rise over run. So we rose 21 times 10 to the negative 11, and we ran 6. Right? Is that correct? Yeah. Whoops. Because we're using the line of best fit here, and we know we have to start at 0 based on our ecuaciones. So what we get is, let me just plug this all into the calculator here. We get 21 times 10 to the negative 11 over 6. Now we have to divide by epsilon 0, which we can calculate, sorry, not calculate, find, listed here. Epsilon 0 is 8.85 times 10 to the negative 12. So this implies 3.954. Implies K0 equals 3.954. And let's see, should it have a unit? I'm thinking, where are we? Excuse me. Here we go. I'm thinking that no, it should not have a unit. It's just a scalar. Let's use our classic color. All right. Now we can get back to where we were going before, with only 5 minutes left in the question. So let's hope we got it down. Okay. So now we're on part D. Let's use that red though. D. All right. So we now have a capacitor of the same aluminum foil plates and just one sheet of paper. Using the experimentally collected dielectric constant, the phone rings. The student collects the capacitance to be 18 nanofarads. The student uses this uncharged capacitor to build a circuit using a wire, a 36-volt battery, 3 identical 80 ohm resistors, an open switch as shown in the figure above. Calculate the current of the battery immediately after the switch is closed. So immediately after the switch is closed, the capacitor doesn't really affect stuff, so the in parallel resistors become 81 over 1 over 80 plus 1 over 80 is 40, plus another 80 is going to be So our total is going to be 1 over 80 plus 1 over 80. These are all ohms, plus 40 ohms, 80 ohms, sorry. And that came out 20 ohms. So, nice Ohm's law application tells us the current is going to simply be 36 volts over 120 ohms. What is 36 divided by 120? 0.3 amps. Okay. And let's move fast now. Determine the time constant of the circuit. Tau is equal to RC. The combined resistance is 120 ohms, so we have, so we have 120 ohms times a very small 18 nanofarads is, well, let's calculate 120 times 18, 2,160 nanoseconds. And if we were to convert that to a different unit, what is it? Goes nano, micro, right? So yeah, we go nano to micro for 1,000. So we can say that this is equivalent to 2.160 microseconds, which I have to write like this, or else it's milliseconds. Cool. Let's box him up. All right. Let's go back down. All right. Final part. 2 minutes. Part F. Students A and B measure the time it takes after the switch is closed for the voltage across the capacitor to reach half its maximum value and find that it is longer than expected. Student A assumes the capacitance value is correct. Would student A conclude the resistance value is larger or smaller than measured? And explain what could account for this. So here we've got larger, here we've got smaller. So if the time it's taking to fill the capacitor is too long, that means that there's more resistance than one would expect. What could account for this? Well, the battery could have an internal resistance. That's one example. Battery could have an internal resistance. And perhaps that internal resistance is much higher than it was thought to be. And that would account for the capacitors taken forever to charge. Student B assumes that the resistance value is correct. Would student B conclude the capacitance is larger or smaller than measured? Larger, smaller. So, I gotta think about this. If the capacitance were larger, then it would take more, it would be able to hold more charge. Let me peek at the equation sheet briefly. Because the total energy stored, of course, goes up with capacitance. If you gotta put more energy in, it's gonna take more time. So I would say then the capacitance needs to be larger. This is possibly incorrect. And what could account for this? Well, it is possible that the capacitance could be nonlinear near zero. Could be nonlinear near zero, with respect to the dielectric that we're placing in. This single sheet of paper. This again might be complete garbage. We'll see. All right. Question 3. The figures above represent different views of two long straight horizontal wires, 1 and 2, carrying currents I1, I equals I, I2 equals 2I, respectively in the directions shown. Wire 2 is going left. Oh, and wire 1 is going out of the page. Sure. Okay. Yeah. I see it. Wire 1 and point P are distance. Okay. Carrying currents, blah. The wires are held in place. The current is directed out of the page. Wire 1 is a distance D. P is a horizontal distance D from wire 1. Distance, yeah, okay. Use Ampere's law to derive an expression for the magnitude of the magnetic field at point P due to wire 1. Question 3. A. Ampere's law says that the line integral of the magnetic field is equal to mu naught times the enclosed charge. So, if we were to calculate the magnetic field at point P, you need to consider wire 1 and wire 2. So, what is going on with my... Oh, I'm in eraser mode by accident. Why am I in eraser mode? Okay, so we would need to say the line integral around wire 1. So, wire 1 is going to be contributing the magnetic field from it times 2 pi d, which is that radius, assuming it's going to be equivalent, which it will be because it's very long. We're given that. Is going to be equal to mu naught times the enclosed charge. That enclosed charge in wire 1, sorry, current is going to be I, just I. And from wire 2, we're going to get that the second magnetic field is going to be 2 pi, and it's also going to be a distance d away, but now mu naught 2I. And this is only an expression for the magnitude of the magnetic field. Oh, excuse me, this is only due to wire 1 in part A. Makes much more sense. So, therefore, we find that the magnetic field from wire 1 has magnitude mu naught I over 2 pi d. Now we can get into the actual complicated stuff. Derive an expression for the magnitude of the net magnetic field at point P. So, we have from wire 2 that B2 is going to be, well, let me actually erase those strange squigglies. We have that B2 is going to be mu naught 2 mu naught I over 2 pi d, but they're going to be pointing in different directions. And specifically, the one from wire 2, if you right-hand rule, is going to be pointing into the page at P, and the one from wire 1 is going to be pointing up from the page, looking at figure 1. So they're going to be perpendicular. That's all we really need to know. So if we call u naught I over 2 pi d, we call this like alpha or something, our vector is going to look like alpha 2 alpha 0. And the magnitude of this is just going to be root 5 alpha. So this tells us that the magnitude of B net is going to be equal to root 5 mu naught I over 2 pi d. Let me just check one thing with the handy dandy equation sheet. Yeah, we're good. All right. Part C. Is this the end of the test? No, there's mucho más. Let's hope we can get through it all. Calculate the numerical value of the angle to the horizontal for the direction of the net magnetic field. The angle to the horizontal at point P. What is the the horizontal. I'm assuming that's for wire 1. I see. Horizontal distance d. So the angle from that horizontal, well, the angle from the horizontal that we're really considering is a 1, 2. The 2 is going to be coming from I2. And that 2 is going to be the one pointing into that page. So basically, this whole triangle here is going to have base of 2, height of 1. Yeah, okay, got this. And so our angle theta is going to be the arctangent of 1/2, which is approximately equal to arctan 0.5, that many radians. Let's multiply that by 180 over pi, and we get 26.54 degrees. That will be our angle from the horizontal. Wire 1 is now released. Which of the following best describes the initial motion of wire 1 due to the magnetic field of wire 2? Assume gravitational effects are negligible. So here they've got lots of options, so I'm just going to have 1, 2, 3, 4, 5 for my check marks. 1 is wire 1 will not move. That, I see. To move. So wire 1 is released. Wire 2 is going to have a magnetic field, and the magnetic field is going to spin wire 1. I see. So if we do the right-hand rule, wire 2 is going to be pushing into wire 1. And that magnetic field is going to spin it, but not in any of the given axes. Wire 1 will move. So we can safely cross out 1. It will not move directly upward or downwards. It's going to be one of 4 or 5. Will it rotate clockwise or counterclockwise? I am at a loss. I think that because wire 1 is pointing this way, it's going to have its own magnetic field, which is going to, the current, that is. So the current is going to take a cross product with the, so the magnetic field is coming into the wire. So that's a downward. The current itself is there. So the current is going forward, and the current is going forward, the magnetic field is going downward. It's going to rotate to the right, which is to say that the current is going downward, the current is going this way. So the current is going downward, and the, wire 2 is going, so I'm doing a lot of right-hand ruling here. Right-hand rule says that the current is going to go down there, which means down there, and there. It's going to rotate counterclockwise. Justify. Gotta write fast. Justify. It's going to be that wire 2 creates, it's going to be magnetic field into page on figure 2. Current cross current of wire 1 cross the magnetic field. This is going to be the cross product with magnetic field implies counterclockwise rotation. Okay, that's decent. Hope I'm right. Alright, wire 1 is now placed by a conducting rectangular loop of length L with W resistance R. The loop is placed at a distance D from wire 2 as shown. Okay, conducting. The loop wire and distance D are all on the plane of the page. The long side of the loop is parallel to the wire. The current I2 for the wire is decreasing linearly as a function of time according to the function I2 equals 2I0 minus KT. K the positive constant with units negative inverse seconds. That's all well and good. So here we're on part E. Of the following, select the integration. We'll give the expression for the flux as a function of time. The magnetic flux is going to be the integral from, it's going to be from D to D plus W. That already removes, so let's call this A, B, C, D. That already removes B and D. Get rid of them. Will it be divided by 2 pi r, LW over 2 pi r, or not? It's going to be divided by r indeed, but it will also contain the length. Yes, it is going to be C, because we contain the r and the L is in there. Given that the flux through the rectangular loop is a function of time t is given by the equation blah. That corroborates our answer. Derive an expression for the magnitude of the current, if any, induced in the loop. Alright, so magnetic flux is going to be this. The induced EMF is going to be negative with the change in that flux over time, and V equals IR implies that the induced current is going to be this negative derivative over R. We can do this. So this is going to be the negative 1 over R times the derivative of this with respect to time. With respect to time, we've got an L1 over K, so we're going to get, let's take out this factor of K. So we've got negative K, and then that T goes away, and we're going to have mu naught I naught L over pi Ln of D plus W over D. This is our expression. Yeah, okay, that's it. And that came from doing that differentiation divided by R. So let's not box it yet. What is R? R is, I don't know, we're just given R, never mind. Let's get to the final part without my drawing program destroying me. What is the direction of current if any induced in the loop as seen in figure 3? Blah, okay. So this is clockwise, counterclockwise, undefined, justify. Alright, this is part G, this is part F. So we have a magnetic field, if we do the right-hand rule, going into the loop, and that is decreasing with time. Current in wire 2, ooh, yeah, okay. That's decreasing with time, so it's going to be getting less strong in the into the page direction, so it's going to want to go more strong into the page direction, which means it's going to be a clockwise, and it's going to be that decreasing flux into the page from wire 2 implies by lens that there's going to be an opposing change. that implies counterclockwise. And we can't write a better explanation than that because our time is up. Well then, it would have been nice to go a little faster so that we could have written out a more complete explanation. But we didn't have time. Let's grade this. Let's see which mistakes I made and where I made them. AP Physics, C&M. This was the 2018 exam. Let's go ahead and look at the scoring guidelines. This will be fun. Let's start here. And we can't use a red pen to grade, unfortunately, because we used a red pen to solve. So let's use this nice greenish pen for our grading. We haven't used it before. All right. So the solutions contain the most common method. They also contain an alternate solution sometimes. Generally, double penalty for errors is avoided, so try to maintain consistency. Implicit statements of concepts normally receive credit. The scoring guidelines accept gravity. Okay, that doesn't matter. Strict rules regarding significant digits are not usually applied to numerical answers. All right. So we already failed somewhere here. Oh, and I know exactly where also. I am so silly, aren't I? Well, in the future, let's try to actually integrate. So in our teacher's marker, you guys were probably smacking your foreheads. What is the integral of r cubed? R to the fourth over 4, not r cubed over 3. Ah! I was probably looking at this integral over here or something, if I had to make an excuse for myself. So, if we're using the integral to determine the charged enclosed, Q enclosed is rho dv is br dv. I guess we get that point because, like, we set up the integral correctly. Well, actually, no, we don't get that point because all we did is we substituted dv. So we got to write this out. We got to write out somehow that Q enclosed is equal to just the integral of rho dv. That's a point. We don't get that point, unfortunately. So we get the substitution point. Yes. But we don't get the correct answer point. We get plus 1 of 3. That is sad. For the first part I. And somehow. Oh, but lucky us, all the requirement asks for is an answer consistent with part AI. So luckily for us, we score plus 1 out of 1 points, even for an incorrect answer. How generous of the College Board. Use Gauss's law to derive an expression for the magnitude of the electric fields in the following regions. So I should have remembered that the electric field only increases linearly if you have a uniform charge density. This entire question is going to be incorrect because of the silliness. And I remember at the start when I had the answer, I said, is this right? And then I just nodded to myself and said, yeah. Nope. Use Gauss's law to determine an expression for the magnitude of the electric field in the following regions. Yeah, no. So for correctly substituting the area of the Gaussian surface into the integral. So, first of all, yeah, we get that part. This is plus 1 point. And the second point is for correctly substituting the charge from part AI into the equation above. So again, somehow we're scraping through here, getting points despite our horrendous misstep of not integrating. For correctly substituting the charge from part AI into Gauss's law to calculate the electric field. Again, somehow we have earned a point for this guy also. I don't think I really deserve it, but College Board says I get it. We will definitely not get points for the graph, though. Determine the charge on the inner surface of the conducting shell. An answer consistent with part AII must have opposite sign. Alright. Seems like they're saying that I get a justification point because I put that the shell is equal to 0, which is charge enclosed. Oh. So to earn their justification point, I would have needed to say the electric field in the shell was 0. So what I'm learning is that while I'm justifying this fine in my vocals, I need to also write it down in order to get the points. So the justification, no, but somehow we're still scraping through getting points for being consistent with our wrong answer. Luckily, we are correct on part 2 because, or sorry, part CII, because there was not much to that question. And for a concave, yeah, this graph part, rip. For a concave up graph that begins at the origin and increases r equals a. For a concave up graph that is continuous with the first section and decreases from a equals 0 to a non-zero value. So we get +1 for this part. For a graph with e equals 0 for r greater than b, we get a point for that. Yeah, okay, so we get 2 out of 3. And the graph should have been basically a parabola going up there. La la la, this was silly of me. For ranking that y and z have the same potential, got it. For ranking the potentials w greater than x, w greater than x, which is greater than y, and z. Yeah. Okay, we get +2 out of 2. So that was a very silly mistake to make, to not integrate. And when I take the test on Monday, I hope I don't make it. But on the bright side, the College Board is kind of nice in allowing consistent answers to get through. So let's tally up our points. 2 out of 2, 4 out of 5, 6, sorry. We have 2, 4, 5, 6, 7, 8, 9, 10, 11. Okay. So the final tally for question 1 is 11 out of 15. And we could have had 15 out of 15 because our logic was all correct. We just didn't integrate. And I'm saying we, but I mean me. Alright, I'll fix that up for the exam. Okay. Let's look at question 2. Alright. Part A. For indicating variables that will create a straight line whose slope can be used to determine the dielectric constant of the paper. So, vertical axis C, sure. Horizontal axis 1 over D. That, in hindsight, would have been a much easier way to do this. I put A over D. I think the note says I would have earned full credit if the axes are reversed or if they use another acceptable combination. A over D is linear with respect to... A is a constant, so I should have probably done 1 over D, but I didn't. And that, I think, would still be okay for the purposes of their question. So, +1 of 1 for part A. Plot the data points, indicated in part A on the graph below. Clearly scale and label all axes, including units if appropriate. Draw a straight line that best represents the data. 1 over thickness, so 1 over meter. So they had 1 over meter because I'm area over distance. I am just meter. For a correct scale that uses more than half the grid, I think we line up there for sure. For labeling the axes, including units, I think I got that there. For correctly plotting the data, it looks like we did that pretty well. And for drawing a straight line consistent with plotted data, sure, yeah, that looks reasonable. Cool. So we actually did pretty well on that plotting part. And it looks like I didn't write in that this was part B, so let me just draw in this is B. And hey, we actually get some points. Plus. Alright. part C, which again I did not draw in. Using a straight line, compute a dielectric constant for the paper. For correctly calculating the slope from the best fit line, and not the data points, unless the points fall on the best fit line. Interesting. I can also use points that fall on the best fit line. So the slope, which is going to be, they're calculating their slope to be something slightly different. So we found our slope to be this. Then I think a problem that I had was that I assumed that it would go down to the origin, which is not necessarily true. I think a better line of best fit would have been, no, actually it does look like it goes down to the origin, pretty much. Maybe something like this. No, I take it back. That's pretty good. They calculated it slightly differently and got a slightly different answer also. I always seem to be a little bit off when I'm calculating my stuff, which is confusing to me. Why I'm always a touch off. I'm also pretty close. I would say I definitely correctly relate the slope to the dielectric constant. In my case, my slope already contains the a, so it's just k epsilon 0. And so I definitely get that point. I don't know whether I get the first or last points. Assuming that I know I'm close, I'm going to give myself one of them. Don't know really which one. Like, I know I maybe got a correct answer point. Maybe I got the slope point. I'm pretty sure I'd get at least one. But then again, to be extra harsh on myself, let's give myself neither. So I get only 1 out of 3. I apologize for all the deliberation. I'm trying to be fair and harsh on myself so that I don't get too proud. D. Calculate the current in the equivalent... calculate the equivalent resistance for the parallel guys. So that's our 1 over 1 over 80 plus 1 over 80, 40. For using Ohm's law with the potential difference across... Let's scroll to the right. For using Ohm's law with a potential difference across a capacitor equal to 0. Yep. 36 over that. For substitution of values for resistance, including the value of combined resistance above. And so we do indeed get the correct answer. I think we get all the points here because we didn't explicitly calculate the equivalent resistance, but it is right here. So I think this part D is a 3 out of 3. Determine the time constant. And this time, we actually get an exact answer, thank goodness. So we do get 2.16 microseconds, and that is 2 points. Feels good to get a little something. I wonder why they switched to the tau font there. All right, part F. Student A assumes the capacitance is correct. Would they conclude the resistance is larger or smaller? Larger. With the appropriate explanation, the battery is not ideal and has internal resistance. The actual resistance for the circuit is larger than the measured resistance. Bam. That's a point that we definitely earned. Part 2. Larger. For an appropriate explanation, some of the sheets of paper may be thinner than expected, so the actual capacitance for the circuit is larger than the measured capacitance. That's odd. Sorry, that's an odd explanation. To be honest, I think my explanation is totally odd also. I don't think that's a very good explanation, but it's, you know, I should think of that more as just saying, like, maybe they measured it wrong. Alright, I'll take that into account. They measured it wrong is a good explanation. to be safe, I'm going to just not give myself this point. All right. That's question 2. Let's count up points we got. 0, 1, 2, 3, 4, 5, 6, 7, 11, 12. Is the total. Question 3. Question 3. All right. Use Ampere's law to derive an expression for the magnitude of the magnetic field at point P due to wire 1. All right. We've got our Ampere's law. We substitute in 2 pi d, mu naught I, and we get a correct answer. So we get plus 2 out of 2 on A. Derive an expression for the net magnitude of the net magnetic field at point B. All right. For indicating that B2 equals 2B1, indeed we do indicate that. That's 1 point. So, yeah, we indicate that, as they showed here. For an indication that the magnitude of the magnetic field is the vector sum of B1 and B2. I think this is a fair indication of that fact. And therefore that B net is the sum of squares, so root 5. I think that's fairly clear. I think that's plus 2 out of 2. We get the correct answer also. If anything, I could say I could have just written down vector sum or something, and that would have made it extra clear. And I could have done my square root. So I could have done vector sum, so the square root of 1 plus 1 squared plus 2 squared is the square root of 5. That would have just made it extra clear for whoever was grading it. That wouldn't care like I care and would just be going quickly. For correctly relating the angle of the individual magnetic fields. So what I should have done is I should have explicitly written out theta. I don't like that theta. I should have explicitly written out that theta is the inverse tangent of B1 over B2. Instead of just writing it out with this triangle. This triangle is good. I could have just written it as B2 here on the bottom, B1 here, and theta. For substituting B1 and B2 into the equation, to get the arctan of 1/2 being 26.6. Wait, 26.6 degrees? Or whatever, it's close enough. Yeah. Unfortunately, I'm only going to give myself 1 point there. I don't think I was clear enough why it was the arctangent of 1/2. Okay. Looks like we totally bombed the next part. So what I should have said is, so in figure 2, the top portion of wire 1 will be in a magnetic field into the page from wire 2, and thus will experience a force to the right. The bottom portion, yeah, so I should have detailed how it would create rotation. And I said it would rotate in the wrong direction. Now, I definitely don't turn the first point. The second thing is that it is just saying to state that there's a net torque. And I should have definitely used the word torque, because that is the physics way to say it. Yeah, I didn't state that there's a net torque which causes rotation. I just said that there would be rotation for a kind of ambiguous reason. So 0 out of 2 for this question. And to improve on that, what I could do is, because I think I had it in my head, is that I could have said all of the stuff about the magnetic fields and the cross products, just that it switches the force switches direction over the axis, and so it would cause a net torque, which would not move the wire, which would not translate the wire, which would cause zero translational motion in their phraseology. Zero translational motion, but yes, a rotation. All right. We do indeed get the correct selection here. You get 1 point there for part E. And something happened here. Oh my gosh. I am so silly. I did everything right, but I forgot my negative sign. For attempting to take the time derivative of the magnetic flux to calculate EMF. Also, one thing that I definitely need to remember is that I should just calculate this separately. I should have said equals and then blah, 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 whatever, and then plug it in. Keep it separate, then recombine it. Anyway, looks like we're just doing magnitude anyway, and I should have caught that as my magnitude, but oops. Can't be negative if it's only a magnitude. So for attempting to find the EMF, I mean, yeah, my answer is completely correct. It's just it's all negative. So the two things that I would need to do for this problem are keep my variables separate until I use them, and second of all, to simplify my final answer. Simplify my final answer so that people can easily read it. I do divide the EMF by the resistance to calculate the current. So that's definitely a point. I do not have a correct answer, unfortunately. I have a negative sign, which I should have not put, but I was under time pressure. And I do attempt to take a time derivative. I don't know. I would say there's a high likelihood that I would get the time derivative point. Then again, I'm not specifically saying I was calculating EMF, so going with that rule, when in doubt, don't give yourself the point, because you'll give yourself higher hopes than you have, and you should have. Let's give myself none of those points that I did not explicitly earn. G. For selecting clockwise with an attempt at a relevant justification. Definitely attempted a relevant justification, so I get that. For indicating that the flux inside the loop will decrease. Yeah, I did indicate that. For using Lenz's law to relate the decrease in the flux to the clockwise. Technically, I did that. Because the current in the wire is decreasing, the flux in the loop will decrease. Decreasing flux into page from wire 2. According to Lenz's law, the induced current should create a magnetic field to oppose this decrease. I agree. Thus, the induced current will be into the page, and the current in the loop must be clockwise. I don't know. I did definitely indicate that the flux inside the loop would decrease, so I'll just go play it safe and give myself 2 out of 3 points. Even though, like, technically, like, all the words are there, it just makes 0 sense because I needed 20 more seconds to write grammar. Let's count up our points. 2, 3, 4, 5, 6, 7, 8, 9. So this was 9 out of 15. Not as great. If I had a little more time, I could have justified this better. If I had a little more time, I might not have been rushed here and I could have simplified. And so it seems like the things that I need to work on, hopefully before taking the exam, although the goal is always to learn, so after would be fine also. What I need to work on is, first, budgeting time a little bit better. So I have an idea for that, which is that instead of allowing myself 15 minutes per question, I'll allow myself 14 minutes per question. And That will keep me on my toes. Then we have, also, hopefully when I'm actually taking the exam, I won't actually have to write out all of the questions like the graph, and that will save some valuable time. Another way that I could improve would be to explicitly write out, so explicitly write out reasoning and exactly what I'm doing. My thinking is like this theta one would have been so easy to get a point by just saying, okay, right, it's a vector, you got to calculate the angle, take the arctan. But I didn't really say that, I just did it in my mind. So explicitly reasoning and writing math. And finally, it seems like it's my old friend, it always comes back to me at some point. No silly mistakes. I don't know if I'll ever cure myself of them, but I can try. So what is the integral of r cubed? No, it's not r cubed over 3. It's r to the 4th over 4. All right. Thanks for watching, everyone. And if you're taking APs, good luck with them too. Bye.